right, so in section 6.1, we're going to look at some applications of the law of sines. So one application is we can use it to help us find the area of any triangle. And generally, we already know the formula for the area of a triangle, right? If I give you a triangle here and ask you to find the area, you just take the base times the height, multiply those together, and divide by 2. Right? So area is usually 1/2 whatever the base is times the height, and we have the area. Problem comes is when we don't necessarily know what the height is, right? Generally, we have information about the sides, but maybe we don't know what the height of the triangle is. Then we can start using what we know about sine ratio to help us out. So let's just assume that I gave you C, right? Maybe you have A and B, but you don't have the height, right? So we would say, okay, well, the area is 1/2 the base is C times the height, but we don't know what H is. That's okay because we do know how to find H using sine ratios, right? So we could say, well, maybe I don't know what H is, but I do know that H is the opposite of angle B. Let's take angle B. It's the opposite of angle B. So if I were to use sine, it would be sine of angle B equals H over A, over the hypotenuse. Right, so I'm going to just come over to this side here and say, well, we know that sine of angle B equals the opposite side over the hypotenuse. And we're looking for H, so we just have to multiply both sides by A. So we get A times sine B equals the height. Right, and that's just from because of the fact that we have our little right triangle here. We can use what we know about sine. So really what we're looking at is even if I don't know H, I don't know the height, I know what A is, I know how to find sine of B, I can plug that in here. So we have our formula is 1/2 the base times this expression for the height, which is A sine B. Right, so the area formula that we're looking at now is basically used when we do not know what the height is. We know some other information, some other side lengths, we just don't know the height. Okay, so there's actually 3 forms of the formula that we can use. And we don't have to derive the formula every time. That was just an example of how we even came to these formulas. This is the formula we know of, 1/2 base times height. But if I don't know the height, we have to go and use areas 1/2 BC times sine A, or 1/2 AB times sine C, or 1/2 AC times sine B. Now, which one of these do we use? It really just depends on what information we have. If I know the base and the height, I'm definitely using the original formula. Doesn't matter what my triangle is. But if I know 2 side lengths and an angle, then I'll start to use the other formulas when I don't have the height. Okay, so this example here says find the area of a triangle with the given information. We're given that an angle B is 130, a side A is 62, and a side C is 20. All right, so let's go ahead and draw the triangle. Doesn't have to be perfect, but I'm going to put here, A, B, and C. We already know that angle B is 130 degrees. We know that side A, so across from angle A, is 62, and side C, across from C, is 20. All right, so we're looking for the area. We don't know the height, so I have to use a formula that tells me what the area is without knowing the height. Right? I know side A and C, so I'm coming over here, and I actually know I know angle B, so I'm going to use that formula. So area equals 1/2 A times C sine of B. I can't use the other information unless I have these measurements to plug in. So I'm going to the one that I actually have all the numbers for. So I know that A is 62. I know that C is 20. I know that I know that angle B is 130. All this, I'm plugging into my calculator, and I have the area. So we have 1/2, I'll put 0.5, and then times 62 times 20 times sine of 130, which is 474. 474 point about 95. Right, we weren't given any units. We weren't given inches or feet or anything, so we can just say units squared or square units. All right, let's look at another example. This example is asking us for some information, but we're not really given a picture, so we have to come up with our own picture and then use what we know about the law of sines to help us out. All right, so it says here a circular arc, right? So some kind of circular shape. A circular arc of a railroad curve has a chord of length 3,000 feet and a central angle of 40. So that's really going back to our geometry of what's a chord, what's a central angle. Okay, and our job is to find the radius and the length of that arc. Okay, so we're saying there's some kind of railroad, railroads go and then it curves. So there's some kind of railroad that's kind of curving. I'm just drawing the two tracks, right? So there's some kind of railroad that's curving. And what this says is within that curve, there's a chord length. And a chord length is not necessarily diameter, but it's one side of my circle to the other side. It'd be nice if it was the diameter. Diameter is actually a special chord, right? A specific chord. But it's just one side of my one side of my circle to the other. May not be right in the middle. And it does say that this length is 3,000. So I'm going to put in here 3,000. I'll write it this way, 3,000 feet. And then it says that my central angle, so that means wherever the center of the circle is, right? If I draw a radius out from the center, this angle here is 40 degrees. So that's what a central angle is. I have a circle. If I go from right in the center of my circle to the two radius points, I get 40 degrees. Okay, so I'm going to draw that triangle on the side here. We have 40 degrees here. We know that this long piece is 3,000. So we're asked to find the radius, which is r, right? Radius is the same all throughout your triangle. So those sides are r. And we're also asked to find the arc length. So I'm going to say from here to here. So we'll use the arc length formula that we talked about, I think in chapter 4. All right, so first let's just look at the triangle that we have. Okay, we have a triangle where two sides are the exact same length because they're both the radius of the circle, which means I have an isosceles triangle. So this angle is congruent to this angle, right? And if I use the fact that all three have to add up to 180, if I take 180 and subtract 40, I get 140, right? And then I can take that, because that's the sum of both of these, but I can take it and divide by 2 because these two are supposed to add up to 140, but they're also supposed to be the exact same angle. So I can take that, divide by 2. All right, so I have all my angle measurements, and now I'm asked to find the side length, the radius, which I can just use law of sines. I know one side, I know the angle opposite of that side, right? And I'm asked to find another side with me knowing the angle opposite. So I'm going to say sine of 40 degrees over 3,000 over its opposite side equals sine of 70 over its opposite side, which is the radius, which we don't know. So we can cross multiply. R times sine 40 equals 3,000 times sine 70. We'll divide both sides by sine 40 so that I can get R by itself. Sine 40. And we have that R is, when we type that in the calculator, some decimal number. So we have 3,000. Sorry about that. All right. We have 3,000. And then sine 70. All that's going to be divided by sine 40. So we have that R is 4,385. 4,385 point about 71. All right, so that's my radius here. And then I was also asked to find the arc length. And so, I'll circle this. Arc length is, we label it with S. It's just the radius times theta. But theta, or the angle, I'll say, does need to be in radians. So we have 40, we need to just change it into radians, right? So if I have 40 degrees, just going to put here 40 degrees. To change that to radians, we were using the fact that pi over 180 is equivalent. So we can use that and change this to radians. Okay, so I'm going to leave that in parentheses. And then we're supposed to multiply by the radius, which we now found is this 4,385 number, 0.71. All right, so our arc length is going to be this times our angle in radians. So if I plug all this into the calculator, we already have this number here, so I'm going to leave that and multiply by 40 pi. Multiply by 40 pi and then divide that by 180. So we get that the arc length is 3,061.80. All right, so our next lesson will be on law of cosines, which is next week. So just look through law of sine for now, get familiar with it, and see if you have any questions for me for next Wednesday. Or, of course, you can email me questions.